Welcome everyone to this new video tutorial in using ArcMap, and in this tutorial I would like to show you how to georeference images or also maps in a special version of the image to image georeferenciation. So we will start with a blank new map or a blank map in ArcMap. So just open ArcMap. You will be presented with this selection. So go to new maps, my templates, and there we are. No, we don't want to save it, so that was from my last session. And as you can see, you don't have any projection information available in this new this new project. So first of all, what we will need a reference set or reference image which already has a projection information available in the file, and then we will need the other thing, the map or the image or the aerial image or whatever you would like to connect with geodata. So first of all, we will go to the folder where the data is. So I will now georeference this map. This is a Berlin map, and as a reference set I will use Landsat data from 2000, year 2000. It's Landsat 7, especially band number 8, so it has a spatial resolution on ground of about 14 to 15 meters. I will add now only this one layer to the project, so it's path number 193, row number 23. I think I can link this file in the YouTube video. So Berlin is over here, so there's the inner part of the city. There's a former Berlin Wall here, I think. Oh no, it is here. So this is Potsdamer Platz. There you have the Brandenburger Tor, the Spree, Tiergarten. So the inner part of the city. And if you're looking here on the lower right corner, there are coordinates available. So just check one more time with right click on it, properties, and go to source. And in this source section, especially here in not in raster information but in the spatial reference, you can see that this image has the projection information WGS 84, so that's the projection, UTM zone 33 north. Oh no, WGS is not the projection, it's just the ellipsoid, and we have a spatial resolution of 14 meters, I think, something like that. So yeah, we will now just press OK. So we already have the information. Now we will add the second layer. This is Berlin 10,000. That's just a map. And when you will go to zoom to layer, there it is. So on the upper left corner of that image, there's the origin of the whole project. So on the upper lower left side, there's a center of the whole projection. So this file has no projection at all. You can check it here. Spatial reference is undefined. So we would like to address each pixel with a geo information or with a location. So we will in the end we would like to come up with a map or with a file where each pixel has a coordinate. So just go back to the full extent of that thing, zoom to layer, and as you can see here, so we will zoom in one more time. This is the inner part of the city. There's something like, let me explain, this is the Mitte region. I think there should be the Brandenburger Tor in the upper part of the image. Yeah, there it is. Here's the Brandenburger Tor, here's the area of the Reichstag, and here's the Potsdamer Platz. So this map has to be georeferenced. Therefore we will start now with a special toolbar here. This is called georeferencing. If you cannot see that toolbar, just right click here in this one and search for georeferencing. Or you can also go to in the former version it was tools. I think now it should be something like customize toolbars, and then just click on georeferencing. So what we will need to do, we need to first fit that image, this map, to the screen, to the region where we would like to see that image. So we will now just zoom out a little bit to get an idea about the extent of that image. So oh, that was too far away, so like in the fairy tale. That's in a part. So we will go to the now referenced image, right click, zoom to layer, and we will search the extent of the unreferenced image. So it should be located here. Yeah, there's a Brandenburger Tor. And what we will do now, we will choose that layer to be referenced. This is the one, and we will say fit to display. Now the image or the map is fitted into the current display, and now you can see, well, that thing is rotated. So go one more time, flip or rotate. We will rotate it now to the left, and yeah, should be fine for the moment. We will now come to the special part. We will search for certain points, so-called ground control points, in the map, as well as on the satellite image, to connect these points together or with each other. So first of all, I think that the so-called Siegessäule will be maybe a very good ground control point. So there's this Siegessäule right in the middle of that crossing, and maybe you will know that the Siegessäule is not that it has a dimension, so it's not punctual, or it's not a point on the map, so it has a width and a length. So we have to decide whether to take the Siegessäule or maybe something like that crossing here. So there's a special point in that crossing we can try to find on the other map. So what we will do now, we will say we would like to use this tool, so select control points from layer to map. And what we will do now is we will locate a point on the ungeoreferenced map, and we will search for the same point on the referenced map. So we'll use that tool now. Go maybe on this crossing here. You don't have to be so accurate in the first case. Now we will remove that layer, and as you can see, the point is following, and now we will search on the map for the regarding point. So I have to zoom out now. Once more, and there it should be. So go back to the tool. Still it is following. Well, there's some artifact in the software, and we will now try to locate it maybe here. You can now make the map visible again. As you can see, the first point is pinned to the underlying map. What we will do now, we will go to another ground control points and search for another point on the map. Maybe now the Brandenburger Tor, and there should be some good crossing. And we'll try to find the entrance to the place near the Brandenburger Tor on the Landsat image. So we'll use that point. Click here and search for the same position on the map, and that should be somewhere here between that pixels. So one more time, you have to take a closer look on that. Let's reschedule it. So I'll make it visible again. Zoom in, zoom out. Oh well, looks quite nice in the first case. So what are how many ground control points you may need? It depends on the system you would like to apply. So there are several possible methods to georeference it like that. So the normal ones, or the most commons, I think, are the polynomial models. So the system tries to find a fitting polynomial between your input data and the reference data, and there you can decide whether you would like to have a first order polynomial, second order polynomial, or third order polynomial, or you also can use adjust and spline interpolations. So when you're using first order polynomials, you will only need 2 or 3 points. I think 3 points are needed, but 3 points aren't enough. You will need several points, at least 10 to 15, for a good first order polynomial interpolation. You must see that you will create a cloud with your points, and fitting a line through that cloud is much easier if you have enough points. So the overall error will be maybe a little bit higher than by using just 3 points. 3 points will create a 0 order error, but the resulting, or the quality of the result, will be much higher than just by using 3 or 5 points for first order polynomial georeferenciation. So we will go ahead. I will now stop it, and I will present you my ground control points after the break. And yeah, thank you very much for waiting. So I've created now 12 points, I think, or I've chosen 12 points on both maps to represent ground control points. And I've mentioned that you have to choose a lot of points, and you have to search for a lot of points for good georeferenciation. In this case, this have been 12, and there are other aspects to keep in mind by choosing a GCP. First of all, it should be time invariant, which means if you have two, or both images are two representations of your scene at two different time slices. And let's say, well, there's a Berlin map from prior 1989, and then you have a satellite image from 2000. There have been a lot of construction, reworking of the ground. Streets are no longer there where they have been before, and everything like that makes it hard to find good ground control points. Then they should be distinctive, so you have to be sure that it is the same point in both scenes, which also means that you need a good reference set. So in my case, the reference image isn't that good for the input image. The input image here has a scale of about 1 meter, and the reference set has a scale of 14 meters. So it's very hard to identify each pixel in this Berlin map from 1 to 10,000 and find the same pixel or the same object in the reference set. But what else can be a decision marker for having a good GCP or a bad GCP? By creating these points, you will get something like a table of input data and reference data. You can have a look at that by choosing View Link Table, which tells you, okay, these are my input coordinates, and these are my output coordinates. And each pixel or each GCP which has a very high residual, like this one here, there's somewhere here, is not that good represented. So you can have a look at that, say, okay, is that really that correct? It's hard to identify. So this is something like a building, and it's not that good represented in that scene. So you can readjust that point by choosing it. Maybe here, this point, just press delete and go with the second point and say, okay, well, maybe this location isn't that good, so I've created now a new point. And as you can see, the residual, so the difference between the calculated coordinate and the real world coordinated as you are suggesting it by clicking into the map, isn't that high anymore. But it's not like, okay, and now I have to choose and I have to sneak a little bit around and search for good representation, and just everything is about reducing the residual. It isn't. So just make good points, make a lot of points, and that's the best thing you can do. But keep in mind to make qualified points as well. So now you have the input source, the source data, the map data. You have a residual, and then you have something called like a total RMS error, which gives you a value of quality of your georeferenciation. So the reference set has a scale of about 50 meters. The input set has a scale of about 1 meter. And this total RMS error should be less than half of the pixel size of the reference set, which means that in our case we will this is a good representation, but it's not that good. But most of the errors belongs to the different scales of our input and reference set. So if this would be the same scale, the total RMS error should decrease. And then you have the transformation. So if you have chosen a lot of input or a lot of GCPs, you will be able to switch your transformation. But first of all, let's press OK. I will go back to the full extent of the layer to show you what is the difference between these both. So we will go into this one and say, well, we won't use first order polynomial, which is something like a relocation. You can stretch your map and you can rotate your map. That's it. You can do nothing else with that. So it's just a fine transformation. Maybe you should have a look into the documentation of ArcMap to get a better understanding of that one. Then you have the second order transformation, which it will include something like a quadratic term in your representation of the point cloud, and or the interpolation line or something like that. But yeah, it will get you some curvature in the x and y direction maybe. Then you have the third order polynomial. As you can see, you have it's more distorted, but it also reduces the RMS error because it's more easy for the program to choose a third order polynomial to fit your input and output data. And then you have the spline interpolation. The spline interpolation is quite sexy, I think, because there won't be any residuals. You don't have any RMS error in the end. But what does it do, or what does it does, is that it keeps your, or it uses your input data as something like a rubber sheet, and each GCP serves as a pinpoint of your rubber sheet. So there won't be differences in the input and reference data set at these points of your rubber sheet, but you cannot quantify the failure between these points. So that's a down part of it. So I think we should stick now here with the first order polynomial, because yeah, it's such a small area. You don't have to keep in or take into account some kind of curve or curvature of the Earth or something like that. So in this small area, you can stick with a first order polynomial. Then you have the possibility to save your input data set or to load your table. So we'll just press OK at the moment, and what we need to do now is we need to recalculate a new file which already contains that geoinformation. Therefore, you need to just to click on georeferencing, and you need to use rectify. What does it mean, rectify? Rectification is something like a recalculation of the values that build up your image. So every image just contains numbers or values. Each pixel is a combination of 3 different colors, red, green and blue, and the intensities in that colors will create you that RGB color scheme and therefore a colored pixel. And by distorting the image, and we will do nothing else like distorting the image in our case, we will we need to recalculate the pixel, because the former pixel will not fit into the quadratic scheme of pixels in a TIFF file anymore. So and therefore you will need first of all a pixel size, or cell size called, which is here 0.88 meters. I will reuse that with 1 meter because it's much easier to calculate afterwards distances by just maybe counting pixels maybe. And then you have the possibility to change resampling method. First of it is a nearest neighbor resampling method, which tells you, okay, if we will look into both pixel schemes, and the pixel which is nearest to the targeting pixel will give the targeting pixel the pixel value, which means nearest neighbor. So the advantage of that system is that you will keep the values of the pixels, which is quite important for some kind of NDVI calculations maybe in the end. The disadvantage is that you will get something like a blocky image, which isn't that nice to look at. Maybe these both points are the most important. Then you will have the bilinear interpolation type, which means that the new value is calculated from the 4 surrounding pixels, I think, 4 surrounding pixels, and which is something like a low pass filter, something like that. So the image will be blurred out a little bit, but it will change, of course. It will change the values of the pixel. But if you're not interested in the correct value representation, but just in a good representation of the optic or the image itself, it will probably be the best way to use it. So it's set here for continuous data, and then you have the cubic convolution, which will increase the pixel number, which will influence the targeting pixel by their contributing values and calculation of the mean. And so this will blur out the image a lot more. I will now stick with the bilinear interpolation because I'm not interested in the pixel values, and it should be fine at the moment. And I will now use a new name, which is WGS. I think it was UTM-33 North, and the format will be TIFF file because it's most common in the GIS scene. You can use it with open source data as well, open source systems as well. I will use no compression type and just click save. So this has taken some time. What we will do now, we will remove the old file and import, oh no, that was the wrong button. We will import the new file we have just created. And as you can see, there's a blackish blackish area here, so that is due to the format to save it as a TIFF file. There's now a no data section here, so the values are 0. And but what you also have, we don't have that kind of blocky image as maybe by using a nearest neighbor interpolation. And what we can do, beside that numeric value of the RMSE, we can make something like comparison between the reference set and the new calculated image with the georeferenciation image information. To make sure that we have that georeferenciation, we can go into the layer properties, say source and spatial reference, so it is correct UTM zone, and yeah, that's fine for the moment. And we can adjust the transparency of that layer by clicking on display, say transparency to, well, I'll say 50%. Say OK. Now you can differentiate your map to, or compare your map to the real world Lancet data. And as you can see, the Spray River is fits quite nice. Then you have these little water bodies over here in the Volkspark. They are fitting nice as well. Also the harbor here, the new train stations here fits quite nice. Everything seems fine for the moment, and well, it will also represent, of course, by the RMSE, that there won't be any big differences between these both images. So that's for it at the moment. I will present you another video on how to make this georeferenciation more accurate, due to the fact that we are georeferencing a map here. In that case, says you should have coordinates in that map. So if we are looking on the area underneath the map, there's something like UTM coordinates, and you will see an east value, or latitudes and longitudes. So longitudes and latitudes. You will know what I mean. And so you can address each coordinate due to the XMap and YMap values afterwards to the real world dataset. And so we will make another georeferenciation by choosing the correct coordinates. Thank you very much for watching. If you have any problems, or if you are facing some kind of difficulties, just drop me a line. I will be glad to help. Also send me your suggestions for another videos. I will be also glad to serve them. And so yeah, just stay tuned, and I hope you have enjoyed it and you have learned something. Thank you very much for watching. Goodbye.